Okay, should we get started? Okay, all right. Thanks a lot for the invitation to come here. I've been to Brazil before, but never to Natal, so it's really a pleasure to be here. So I'm Eric Popp. I'm with Electrical Engineering and Material Science and Engineering at Stanford. So I was asked to give 2 tutorials and a research deep dive. So today's talk is actually part number 1 of the tutorial, which is pretty broad, I hope. Not just about 2D materials, but in general about nanomaterial applications. And hopefully we'll partially answer that question in the title. And then tutorial number 2 will be tomorrow, a little bit deeper dive. And then tutorial number 3 will be specifically about the research happening in my group. Okay, so usually when I give these talks and I travel, I like to show where I live. I used to work at the University of Illinois, which is about 200 kilometers south of Chicago in an ocean of corn. And then I got tired of the corn, and I moved 6 years ago to the most expensive area in the US. And that's about 50 kilometers south of San Francisco. And so I've been there for about 6 years. So I can literally today say that I've been 6 years there and 6 years at Stanford. These are the postcards from campus. So if you've been on campus, these are postcards. I believe the Hoover Tower is probably the tallest building, or some of the tallest buildings in Silicon Valley. It's got a great view. And I always encourage visitors to climb all the way to the top and take pictures from there. Okay, so as I mentioned, this is sort of the plan. So I think 11 a.m. each day. Today, I'll try to give you my perspective on what 2D materials may be good for. I'm sure I'm going to miss lots of things, and we can debate those vigorously at lunch and over caipirinhas at dinner. And then tomorrow I'm going to talk about some alternative facts about 2D materials. That's sort of a very experimental title and a very experimental tutorial. In fact, I probably spent most of my time working on this one as I was flying here and with my students' help. Literally this morning I was still working on that, and then the research talk on Thursday. Okay, so really quickly, I'll just get right to it. I've been asked to talk about 2D material applications, so I went and I looked up a few of them. These are existing 2D material applications that you can buy. I am told that you can buy graphite lubricant. You can buy molybdenum sulfide lubricant. These are about $10 in the US. There is something called a graphene racket, $200. I believe Novak Djokovic plays with this. I wanted to buy it, but I don't play tennis well enough to merit such a good racket. Then there's a graphene jacket. I'm not sure why it's important that it's graphene, but it's about $700, and it makes you look very grumpy. Maybe because you spent $700 on it. Maybe that's why the model is grumpy. And then there's something that Bill Gates was funding in the UK a few years ago. This is not a joke. I don't know if this is available or not, but I thought it would be funny, especially because I found this image. You don't often see a picture of Bill Gates on a condom wrapper, so I thought this would be fun to put in there. But I don't have a price for that. So these are all composites. I think that kind of tells you something. They're all composites. Okay. Now, I have a colleague at Stanford whose name is Evan Reed. And Evan Reed is a computational guy, and one of the things that he does is he uses machine learning, which apparently everybody does except for me, to discover new 2D materials, among other things. And so he published this paper very recently in Nanoletters, and I think since then he's updated this, and he says that there's over 1,000 2D materials available, right? So this is not just graphene, this is not just MOS2, this is not just black phosphorus. There's over 1,000 2D materials, and Evan and his students have rated these by the band gap. So you can see there's over 150 metallic ones, there's about 160 semiconducting with a band gap that I might care about, and then there's 26 with band gap like boron nitride, right? So not just boron nitride, but about 26 of those. And so my observation was that there's more 2D materials that are Avengers and presidential candidates running against Trump right now in the US, right? So many more, okay? Now, among those, which one will actually be useful? My opinion, this is just my opinion, I could be wrong, is that the 2D materials that have unusual properties and no bulk analog are probably going to be the most successful. As I'll show later, we probably will not replace silicon, because silicon's very good at what it does, but there are some examples where we can complement silicon and so on. Okay, so here's maybe my pet examples. A good example, I think, that specifically takes advantage of the atomically thin nature of these 2D materials. It's something that I happen to be involved with, that's why I happen to know about it, but these are essentially DNA nanopores. So to filter DNA, you actually need something to sense the individual base pairs, right? The spacing of the base pairs is about 3 angstroms. The thickness of 2D materials is maybe the only thing that could actually sense almost every base pair as the DNA, threads through these holes. So I think that's actually a cute application where you're really taking advantage of the atomically thin nature of the material, and you really cannot do this with a piece of metal, a piece of silicon, or something like that. What I think is a bad application of 2D materials is anywhere where we're doing essentially bulk-like. I was talking to someone recently here, actually, and I was mentioning my pet peeve here is to complain about black phosphorus transistors, because people have demonstrated high mobility, relatively speaking, only in thick layers of black phosphorus. And thick layers of black phosphorus don't really make sense because you can do already high mobility with indium antimonide or even with silicon in such thick layers. So it's not a particularly good application, I think, for transistors at least. Okay. As an electrical engineer, I get asked pretty often, can 2D materials replace silicon? My answer is not replace, but complement. I don't think we can replace silicon. I don't think anything will replace silicon. That's like saying, can we replace the wheel, right? We will never replace the wheel. There's nothing better than the wheel, to move around. Really, and I'll say a lot more about this, we work on something called 3D heterogeneous integration. So as I'll explain over the next slides, these are basically integrating electronics on top of silicon electronics to actually make these things hopefully work a little bit better. And I'll give some examples based on memory, some examples based on our own work in 2D materials. And I'll say a couple of things about Moore's Law. My favorite thing to say about Moore's Law is that it's not dead, it's not dying, and it's not even sick. And so I actually prepared a slide about this because, as an electrical engineer, sometimes I get asked to comment on Moore's Law. And I think everybody's heard of Moore's Law, right? Okay. And everybody's heard that Moore's Law is dying, right? Okay. I mean, several times, right? Right. I think it was probably, its demise was probably predicted in the 1980s already, right? And we know what's happened since then. And so I, recently, and I really mean recently, like 3 months ago, in preparation for a different talk I gave this summer, I went and I actually read Gordon Moore's original paper, and then I read Dennard's original paper. And I think this is less well known. But anyway, summarizing this for you, Moore said basically electronics will be about complexity and cost. That's what's going to drive electronics. He never said anything about transistors being smaller. He said complexity and cost. Complexity, of course, can mean smaller transistors. Fine, because smaller transistors means I can make more complex things. But I'm going to argue over the next 15, 20 minutes, maybe 15, 30 minutes, that this is not ending at all. It's actually going 3D, which means more complexity, but building it up vertically. Dennard, on the other hand, gave us a blueprint in 1974. He gave us a blueprint about how transistors actually need to scale down. And indeed, Dennard's law is probably ending, right? In fact, some people have argued that classical Dennard law actually ended in 2005 when we switched from just regular silicon transistors to the high-K metal gate, but we didn't really make them smaller. In fact, things haven't really gotten that much smaller since 2005. Anyway, I think there's great agreement or good agreement that Dennard's law will probably end at the atomic scale, but I don't see Moore's law ending at all. Okay, so a couple of words about computation and computing today. This is a slide I borrowed from my colleague Philip Wong, by the way, who is currently on leave working at TSMC running their research division. So Philip likes to say that pretty much everything in the future will be driven by data. I think there's pretty general agreement on that. And so here's some examples of big data applications. Obviously retail, healthcare, security, genomics, all kinds of things. I'm not even sure what smart cities means, but I put it on there because it sounds cool. So what Philip likes to say is that basically we cannot pursue 21st century applications with 20th century hardware. That's kind of what he likes to say. And I tend to agree with that. And that's because computational demand actually exceeds the processing capability. And I'll give you some examples about why this happens today and where 1D and 2D materials can play a role. So what's the problem with computing today? Everybody's got this problem in their laptops right now, right? You're dealing with this problem every day. This is the reason why your battery runs out when you fly from here to Miami, or even before that. Basically what we have today is we have a separate computing chip. Intel typically makes this. And we have separate memory chips, and those are made either by Samsung, Toshiba, Intel, a bunch of other companies, right? And so these are separated. If you actually open up your laptop, your cell phone, everything, there's a whole bunch of chips, and they're all separated, right? And so what the computing chip does is it actually has to fetch data from memory, back and forth, back and forth, back and forth, literally across the surface of the chip very often. Not to mention, there's a hard drive too, but I didn't draw that. Consider this, essentially, this could also be the hard drive. This could be DRAM, it could also be the hard drive. It's just a general purpose thing. It's obviously a cartoon. So moving data back and forth is actually extremely energy efficient, right? The CPU is always wasting energy, waiting for data from memory. That's like, back in the day when researchers only had, physical libraries. The library was somewhere across campus. You had to walk all the way to the library, find something, retrieve the data, come back to your office, and then do research using that data. That's basically what's happening in our in our laptops and cell phones today, obviously on a much smaller scale. Okay. So my colleague Subhashish Mitra at Stanford actually did a calculation. If you're, I believe this is a genomic application, this is a natural language processing application. I don't know the details, but he's published them. And what he told me is he basically said, look, if you're running through these very, very data-intensive applications, data-intensive meaning the key, right, because you're always retrieving and pushing memory, back and forth, about 5% of your energy is spent actually doing computation, and 95% of your energy, or 82% of your energy, the big yellow slice, is actually spent either in memory or waiting for memory to return data back to you. So you're just, the processor sitting there and just like, twiddling its thumbs, right? So this is a really, really clearly actually a really big problem. Okay, so what's the solution? And the solution is something that we called NEXT. This is a term that we came up with at Stanford, and this is something that we're working on there. Next, of course, just means next, the next solution, right? But we flip the E around because sometimes people do this, and flipping the E around means it's 3D. That's what the E3 means in there. So you'll see, I'll give you more examples, but you'll see what this 3D chip does. And I think you can already tell that what I'm going for is I'm going for this 3D integration of the logic and the memory, maybe even sensors. Oh, of course you're going to need thermal management. By the way, these orange regions are probably thermal management because now you're putting everything together on top of each other. You're going to have to get the heat out, right? So that's going to be a problem. And this is directly taken from this paper that I happen to also co-author, but it's really led by Subhashish Mitra at Stanford. And they've calculated that you could really do this and actually improve computation by about a factor of 1,000. So I'm standing here today telling you that Moore's law is not only dead, but there's actually about a factor of 1,000 improvement that can be done on Moore's law if you bring the memory really, really close. And I really mean within nanometers of the logic, right? The memory next to the logic. The other thing that I want to tell you is that in a way this is not new. When I show this to memory audiences, I have to be very careful to point out that the memory people have been doing 3D integration for about 12 years. Toshiba in 2007 presented a paper at the VLSI Symposium in Kyoto, I believe, in which they presented their idea of basically building memory vertically. And this is currently commercial. Some of you probably have this. If you have a newer laptop or a newer phone, this is inside your phone. You have 32-layer vertical flash memory as the actual data storage, the non-volatile data storage, the stuff that stores your songs, your addresses, your photos, your videos. That's actually gone vertical. It's 32-layer stuff. And companies are already working on, I believe, 64, 96, and I think they're going over 100 layers right now, which is crazy. And then, I was promising somebody at dinner last night that I have at least one Trump slide, and that's my one Trump slide for today. If you look at real estate, on a really serious note, people know for real estate, if you build buildings vertically, they're actually much more energy efficient, right, than if you have individual houses like you have in the American Midwest, which are actually per capita, the energy consumption is much, much larger than the per capita energy consumption in New York City, for example, because you have, you have a shared network for conducting heat and so on, and air conditioning between apartments and so on. Okay. This is, again, a slide I borrowed from Professor Mitra at Stanford. These are, again, his calculations. This is running the Google PageRank application, and he basically shows that if you use a conventional 2D processor today versus if you use this next type processor, which of course has not been built, but it can be simulated, the improvement is not a factor of 1,000x to be precise, but he says the improvement is a factor of 851x. So it's still pretty good. Sometimes I say 1,000 just because it's a nice round number, and I like to round up sometimes. And again, the improvement comes from energy, so it's 37 times more energy efficient by essentially bringing the memory right on top of the logic. And the execution time is also improved by about a factor of 23x. And so that's that little bar over there versus this big bar over here. Okay. So what is needed? I think, you know, I think there's general agreement within the electronics community that this is probably a good thing. We don't know what it's going to cost. You know, we don't know if the reliability will be there. Maybe things will break apart or you know, melt or something because we can't get the heat out. But at least it makes sense that this is probably a good application. So what is needed, and where do the 2D materials fit in? We probably already saw 2D materials written in a few places in those plots. But this thing will need transistors, right? It'll need billions and billions of transistors. Even today, we already have billions of transistors inside our processors. But it's going to need 3D transistors. Transistors actually are built on top of each other. And it turns out you can't do that with silicon very well for various fabrication reasons. And so, and the other thing, it's going to need very, very small transistors that don't leak very much. Right now, we know that transistors really need to be turned off to save power. Remember, this is all about conserving power, too. So you need transistors that turn off really, really well. Silicon's okay, but it's difficult to build in 3D, right? Graphene, of course, is completely out because graphene has no band gap, so you can't shut it off. Carbon nanotubes, maybe. Molysulfide, definitely, because the off-state currents are incredibly good. Certain oxides are also very good. And so this is where some of these things come in, and you know, today's silicon transistors look something like this. I'll show you more pictures. These are called FinFETs or trigates, which are kind of already a weird 2D because it's a vertical 2D fin. But you know, a lot of the silicon people have actually really wanted to go to a 1D, which is really a nanowire. But actually, to me, that looks like a nanotube, right? It's just a wraparound nanotube. So of course, if we could build that, I think there's great agreement that that would be better. Okay, so what 50 years of Dennard's law, not Moore's law. Moore's law was a driver, but 50 years of Dennard scaling has given to us is these FinFETs. These are pictures I took directly from the Intel website or from a Canadian company called ChipWorks, which for a fee will slice, you know, processors and then put these wonderful pictures online. So what Intel called their 22 nanometer Trigate transistor first generation looks something like this. It looks like kind of like this rabbit ears, bunny ears. And they're 34 nanometers tall, 60 nanometers apart, and there's a whole bunch of them, and that was a transistor. And by the way, the current flows in and out of the page. Okay. The second generation transistor, and I happen to know this is inside my laptop. I bought my laptop a year ago, so this is already in there. They've scaled things down, and the fins look like this. So the fin, this is amazing to me. The fin is 8 nanometers wide in the middle. It's about 4 nanometers wide at the top, 11 nanometers wide at the bottom, and you can see every atom. I show this to my undergraduates, and you know, sometimes the undergraduates, they just use their iPhones or whatever, and then they go, whoa, there's atoms in there. Yes, there's atoms in there, right? And so, and you know, we have billions of these. I have billions of these in my laptop right now, and actually they're running this presentation, so they're not working very hard, but that's what they're doing. And of course, this has to be done. You know, already these things have multi-layers. The computing layer is just there at the bottom. Everything else is just interconnects. So these things have like 13, you know, layers of metals just for the interconnection. So it's pretty crazy already. But it is, to me, this is 2D computing because the transistors are all at the bottom. There's no memory. There's nothing really useful on top, just wires, just boring wires. Okay. So what's the problem? We can't make silicon smaller than we've already made it. That's it. We're stuck. And why are we stuck? You know, again, going back to use Philip Wong's words that I used earlier, we're dealing with a 20th century technology. We're dealing with a rock. Silicon is a rock. We've carved things out of a rock as much as we could. But now when we've made these fins, these silicon fins, a few nanometers across, if you make them any smaller, the mobility will basically begin to tank. This is experimental data for silicon mobility for electrons and for holes as a function of the layer thickness. So as you go below about 4 nanometers, the mobility is no longer a few hundred or whatever, you know, it should be for silicon. The mobility actually could be like 10 at room temperature, of course, right? So, you know, basically the electronic properties of these materials become quite bad because of surface roughness. The band gap, by the way, you know, I teach my undergraduates the silicon band gap is 1.1 electron volts. As you confine silicon, you know, into quantum wells, the band gap is no longer 1 electron volt. It's actually significantly higher. And oh, by the way, if you're off by even one atomic layer off, you actually can have huge variability. Now imagine doing this over a 12-inch wafer. Right? Industry has to work with 12-inch wafers. You're off by one atom in one transistor somewhere, and it's going to create these enormous variabilities in electronics. And by the way, that's not only true of silicon, it's true for gallium arsenide, germanium, any of the 3D bulk semiconductors. This is what happens. That's bad for variability. So this is where 2D materials and really, honestly, 1D materials like carbon nanotubes really come in as well. Because, and what we call these 21st century atomically thin materials, because when these are naturally thinner than 1 nanometer, their mobilities are not bad. They're not great, but they're not bad. Carbon nanotubes are actually up here, but by the way, carbon nanotubes also suffer from variability issues just like silicon, right? The mobilities are quite good. So as soon as your diameter of your nanotube varies a little bit across the 12-inch wafer, your mobility actually varies quite a bit, and that's actually based on experimental data. So mobilities are good in carbon nanotubes, but their variability is probably what, you know, not probably, that's actually what's making our life very difficult with carbon nanotubes. The band gaps are here somewhere, by the way. Again, we're dealing with sub 1 nanometer thin layers that have band gaps anywhere between 0, if you really want to work with graphene, to sub 1 electron volt for carbon nanotubes, to somewhere, you know, approaching 2 electron volts, about 2 electron volts for the transitional metal dichalcogenides, such as those listed here. Okay. Again, you know, you can tell I really like this picture because I'm showing it again. You know, I want to emphasize that again, that what's killing this is not just our ability to make things smaller, but the fact that electrically this will actually get worse as you make it smaller. Variability on one hand, and then the mobility gets worse because, as I showed here, this is obviously my cartoonish way of drawing, electrons will scatter from these otherwise imperfect interfaces, right? So, you know, there's obviously silly academics like and Ali Javi's group at Berkeley and others who are trying to see, you know, what we can do with the atomically thin materials, right? And this is some really clever work from Ali Javi using a single carbon nanotube to gate a multi-layer MOS2 stack. And this is work from my group using conventional gates. This is an aluminum gate. It looks huge by comparison, to gate a single layer of moly sulfide. But this is about the best you can do in academic fab right now. The fact that my graduate students were able to build this with e-beam lithography is you know, I mean, we can't really do any better. This is, of course, made by hand, and it's sort of made, you know, one at a time. This is actually something that could be integrated into a real process. In fact, industry can actually do better with these dielectrics than we can. This is 5 nanometers of hafnium oxide. Intel can do 2 nanometers of hafnium oxide without leakage. I just can't do that because I work in an academic fab. That's not that clean. But there's the monolayer thin MOS2 layer. Okay. So what are some of the benefits? I think I already hinted that if everything was perfect, carbon nanotubes would actually be impossible to beat. And so I'm not going to stay here and tell you, first of all, I didn't say that we can replace silicon, but I'm also going to say I don't think we can beat carbon nanotubes. I don't think anything in the 2D world that I've seen can beat carbon nanotubes, because carbon nanotubes simply have such a good combination of mobility and high mobility and low capacitance. Okay, 2D materials just don't have the mobility of carbon nanotubes, and they don't have the band gap exactly, and the capacitance is a little bit larger. Nanotubes just have really, really small capacitance because they are these little tubes. So again, if you take these calculations that Professor Mitra has done with, you know, and compare sort of the best silicon, let's say, nanowires that you could build today with carbon nanotube transistors, you get about a factor of 13 improvement just from switching to carbon nanotubes. So if you could switch tomorrow's Intel processors to carbon nanotubes, perfect carbon nanotubes, of course, you would get about a factor of 13x improvement, which will not translate to a 13 times larger battery life, but, you know, it still makes a difference. And you could operate these things at, this is log scale, and it's missing a bunch of tick marks, but you could probably operate these things at 5 gigahertz if you can get rid of the heat fast enough. So that's good. So where do the benefits come from? As I already hinted just a minute ago, the benefits really come from the fact that we have an ultra-thin body, which means extremely small capacitance. So parasitics are pretty good. And the fact that you actually can push a lot of current. And so very simply, you know, this is the energy delay product that I mentioned earlier. It's basically energy, CV squared, multiplied by delay, which is CV over I. So for carbon nanotubes, C is very low and I is very high. and you can reduce the voltage. Obviously has to be sub 1 volt, but that's sort of a given for these technologies. So basically, you know, if we want to at least replace or complement silicon, we really ought to be looking at materials with low capacitance and high current in the end, obviously. And so, you know, you can scale, if you have high mobility, you can reduce the voltage to get high current, but ultimately the current is what matters. It's not necessarily the mobility, it's if you can get good current, I don't care what the mobility is, because ultimately the contacts will affect you anyway. So you need good mobility, obviously, but you also need good contacts, and you need good, in the end, you just want good current. Okay. So where are we today with these things? So with carbon nanotubes, as well as with 2D materials, growth is a real problem, right? We typically grow things at anywhere between 700 and 900 Celsius, both for carbon nanotubes and for 2D materials, right? And if you show up to the silicon fab with that kind of growth temperature, they don't want to talk to you, right? Because this will destroy all the silicon transistors underneath. The silicon transistors underneath will be destroyed around 550, 500 Celsius is the general requirement today. So what we ought to do, and one thing that we're doing and other people are doing, maybe it's not the best thing, but this is what we do for now, is we grow the carbon nanotubes or we grow the 2D material separately in a high temperature furnace so we can get good quality material for academics. And then we transfer them on a wafer scale, and we can do this wafer scale transfer at 120 Celsius using thermal release tape and all kinds of other things. And we can do this right now for carbon nanotubes. People at Stanford have done it over a wafer scale. So, and then they can go ahead and build the circuits. And the circuits are actually built at relatively low temperature without killing the silicon underneath. Of course, ideally, I would like to be able to grow things directly, right? Transferring things by hand, again, it's okay for academics, even wafer scale, right? We can still publish Nature papers, but industry doesn't like that, right? They really want direct growth. They want direct and low temperature growth, and right now we don't know how to do that. Right now, as I said, some of our best growths, even for 2D materials, are about 700 Celsius. That's kind of high. One thing that we've recently done in my lab with 2D materials that we cannot do with carbon nanotubes is we can actually grow moly sulfide, in this case, directly vertically over a step. So this is the cross section of the wafer here. Right? We've etched into the wafer. We put SiO2, obviously, as an insulator there so we don't short it out. We still have silicon in the substrate there. And then actually it turns out that the moly sulfide grows directly over the step and then down like this again. You can't do that by transferring. You can't do that with carbon nanotubes as far as I know because they're grown separately anyway. This is directly grown on the silicon wafer, just a kind of high temperature. Okay. I think there's some contact problems in here in my mic. I'll try not to touch the button. So why is this interesting? This is interesting because now we can actually build electronics vertically. This is actually a new research direction in my group. I don't have a lot of results to show you, but I'm really excited about this. And it really is a way of taking 2D into a 3D direction, right? By actually building circuits and even data storage vertically. Because this kind of now resembles the memory devices that I showed you earlier, where industry is actually building these silicon memories that are very, very, vertically scaled, right? So that's one way where we're going with 2D materials. We're pushing them 3D, but by direct growth like this, and we can't do this by transfers. Okay. So I want to say a couple of things. You might be skeptical. You might say, this sounds like academic work, but is anybody going to take you seriously? I don't know. But we have some examples. Again, I apologize. These are very Stanford-centric because I work there, and I know the work there a little bit better than some of the work outside of Stanford. This is out of the Mitra and Philip Wong group. This was a carbon nanotube computer that was published about 6 years ago now. That in 2017, they went ahead and they made a multi-layer a carbon nanotube, silicon, carbon nanotube, and then memory, and then more carbon nanotube sensor. So it's like a multi-layer chip. And they also made this on a 4-inch wafer. So this is also, again, for academic purposes, this is as big as we can get is with these 4-inch wafers. And then in my group, we've made graphene circuits, also on a 4-inch wafer. I don't work as much on circuits as my colleagues do, but I love to draw upon their examples. And what we did is here the graphene was grown separately on the copper foil, then transferred for wafer. Should I be using the other mic? It seems very annoying. Sorry. hear me? You can? Okay. Check. I have to almost put it inside my mouth, and I don't want to do that. Okay. Is it okay? I don't want to clip it on my ear. I'll just hold it. Is that okay? Can you hear me? Okay. Is it okay? Okay. Thank you. If you can hear me in the back, then that's good enough for me. So we built these graphene circuits. This is actually a very simple graphene circuit. It was more of a demo, proof of concept, the fact that we can do this with graphene on a silicon wafer scale. And we were doing some simple graphene circuits. These are analog circuits, not digital circuits, but it was still built on a silicon wafer, again, as a demo. Okay, so what it takes to do this next electronics is really, it turns out, not just a bottom-up, and this is where I work, obviously. I work on a bottom-up device level. Mobility, we're concerned, of course, with mobility, on-off ratio, contacts, variability, can we make things variable enough? And of course, we're very, very concerned about integrating new materials, but we also need our systems level collaborators, which we have, to really design algorithms and architectures which actually take advantage of the vertically integrated stack as opposed to what they're used to right now. And of course, I work here, I don't work up there, but this is actually kind of a really combined approach that I think people need to take. And so this is what I showed earlier. I'll probably skip this, but very quickly I'll say that our own little demonstration of, oh, we changed batteries? Okay, thank you. Hello. Okay. So this is louder. I'll have to keep it. If it's too loud, please just tell me. Here what we did, these were actually not even particularly good transistors. These are fairly average transistors, top gates, 1.5 microns, but we can make them wafer scale. The thing is that the function was unique. It was actually an analog integrator of a 4-input vector. What this was, it was basically maybe I didn't write it here. It was a dot product computational matrix. Basically, it was computing the dot product, scalar product of two voltage vectors. And it can do this by just doing a charge integration on this output node right here. And it works at wafer scale, and there's some variability associated with it. But again, for an academic demonstration, we thought this was decent. Another example, this is a collaboration with Philip Wong and Jonathan Fan at Stanford. This is an application where we integrated CVD-grown molysulfide transistors, which have really low off-state current, way lower than silicon, so they win there. And they integrate this with memory cells based on hafnium oxide. Hafnium oxide is used as a memory cell. This is basically what's called an RRAM cell. And this is called a 1T1R type memory cell, one transistor, one resistor. This is actually fairly common for memory. And the cool thing here is that this was done by the students all with a fabrication temperature below 200 Celsius, meaning it can be integrated with silicon, and it's actually okay in that respect. That's another example. Another example, this comes from the Ken Goodson group at Stanford. This is obviously a cartoon. Some of these are obviously real. This is actually a real image. These are real images as well. The idea is when you have one of these 3D integrated chips, it's probably going to be very hot if you don't do something about getting out the power, right? Because you're putting a finite amount of power into a really, really small space. This is already happening today, by the way, but this will be even worse if you put things so closely together. So they're working on what they call this monolithic thermal platform, which would actually include not only microfluidics inside the actual chip. So there should be probably microfluidics built into the chip, not just outside the chip to get the heat out, but also integrating heat spreaders based on 2D materials, which we're working on in my group, such as multilayer graphene, or graphite really, or boron nitride, which is one of my favorites for this activity actually. Boron nitride is probably way, way better because it's also insulating. Speaking of boron nitride, actually, this slide shows up just on time. What I did here is I plotted the thermal conductivity of a whole bunch of materials that we're familiar with as a function of band gap. So far, so good. Of course, graphite is quite good, in plane right there. Copper's right there. Zero band gap, but high thermal conductivity. Silicon oxide, it's quite poor, right? Amorphous SiO2 has a very, very low thermal conductivity, but it's a really good electrical insulator. It turns out if you want materials which are electrically insulating, but also thermally conductive, you have 3 choices right now. There's only 3 choices that I'm aware of: diamond, boron nitride, and aluminum nitride. Diamond is sort of, as you know, very expensive. It's very difficult to grow. I have a colleague at Stanford who grows diamond, but it's not very high quality diamond, right? So she's obviously struggling with it, but it is what it is for now. But the boron nitride and aluminum nitride, especially aluminum nitride growth, actually is quite good these days. It was figured out by the people who got the Nobel Prize for the blue LED, you know. And so people have been growing aluminum nitride for many, many years. Boron nitride and diamond growth is not that good. This plot on the right, by the way, looking a little bit deeper at 2D materials. Here I plot the thermal conductivity of 2D materials as a function of, well, this is in plane. I'm sorry, this is out of plane. And you can see some trends. Obviously, in plane, the thermal conductivities are quite high. Out of plane, the thermal conductivities are quite low. I think for heat spreaders, probably what we care about is just the ones up here, graphite and boron nitride. Everything else is actually a little bit worse. But what we're struggling with right now is, can we grow boron nitride and aluminum nitride at sufficiently low temperature where it can be integrated with silicon? As I mentioned earlier, that generally means 500 Celsius and below. And if so, what are the quality and the thermal properties? And then can we actually maybe leverage the layered material anisotropy like you get in boron nitride or in graphene? Maybe there's something good in there. And so this at the moment, this is mostly simulation work. I've shown, you know, we're doing some experiments as well, but this is just simulation, trying to evaluate, before we spend too much time in the lab, we want to evaluate how these heat spreaders actually work, right, and if they're any good. It turns out there are some advantages. Aluminum nitride, as I might have predicted, is actually better because it's isotropically good a thermal conductor. Boron nitride is only good in one direction, but it's actually quite bad in the other direction, so that's kind of a problem. But in either case, the interfaces actually really become important at high frequencies. This, by the way, these are simulations that one of my students is doing for a 5-layered chip. So these are not just one chip, but it's actually 5 chips on top of each other, a few microns apart, and putting in various heat fluxes and kind of like seeing what would happen if you have SiO2 as the dielectric, as the insulator, I'm sorry, same thing, or boron nitride as the dielectric. And since then, he's actually found out that probably aluminum nitride is the better choice, but we haven't ruled out boron nitride yet. Okay, so this is what I was showing earlier. I'm coming back to this. Obviously, it's a cartoon of a 3D system, but again, just to emphasize, you know, 2D and 1D transistors could be in between those layers. In between the logic layers, we have the memory layers, which could be magnetic memory, could also be, you know, hafnium oxide-based memory. And then these orange regions are where we need to get the heat out. That's where we have to get the heat out. And so I already mentioned the heat, but I didn't say much about the memory. And I really don't have time to talk about memory today, but I just want to say a word about it because it's really, the memory is a part of this. In the end, this is computation immersed in memory. And so just, you know, very quickly, some of the memories that we're exploring, none of these are really based on 2D materials. Well, okay, we have done some boron nitride-based memory recently, but it really looks very similar to the CB-RAM in here, or to the RRAM. So it kind of looks like these two. But these are the materials that, you know, we and others are evaluating. Magnetic memories, STT-MRAM, phase change memory based on germanium, antimony, tellurium compounds. These are, I've already shown these, hafnium oxide, or we've actually done some boron nitride memory work like that. And this is the FERAM, ferroelectric random access memory, that some people work on as well. I don't necessarily know which ones will succeed, but I think all of them are being looked at. And right now, it's this one. It's PCM that is the one that you can actually already buy on Amazon. So this has gone commercial. It's just only 2 layers, not 32 layers or whatever. It's only 2 layers, and it's kind of expensive, which is probably why it's not in our laptops yet. But you can buy it as a separate, kind of like a plug-in, if you do memory-intensive things. Okay, summary and takeaways. So as I said, I wish I had more time to say more about memory, but that's okay. I just wanted to emphasize that there is memory in there, and it is a concern. Whether it's 2D memory or not, I don't know. I didn't do anything, I swear. This is what this thing looks like in the end. You know, there's 3D integration of memory. There's if you need efficient heat removal solutions. You need transistors, of course, and we have experimental demonstrations even at the system level of fairly simple 1D carbon nanotube and 2D graphene and molybdenum applications. And I'll say more about my own work in that area on Thursday afternoon. But here are the takeaways. So if I were to summarize this talk on one slide. First of all, I don't think Moore's law is dead. I think it's just going 3D. I think there are still a large number of energy efficient benefits from computation immersed in memory, from this integration with really, really fine-grained interconnects, and of course we need to take care of the thermal problems. We cannot make isolated improvements. So if I demonstrate, let's say, a better transistor, it's probably not enough, right? We really need to improve not just transistors, but the memory, the thermal solutions, and ideally, I think I said 500 Celsius earlier, ideally everything should be done, this is a little bit more conservative, 450. 450, 500, that's, and of course for academic groups, my colleagues and I have been working on some 3D nanosystems, at least to demonstrate these things so that industry will, take this work a little bit more seriously. So, what's next? Not next, but next, spelled like normal next. I don't have a crystal ball, obviously. I just gave you a small slice of what's kind of been going through our minds at Stanford and with some of our collaborators. But I think there's broad agreement among all of us in this room that if we don't look at new technologies, we just won't know what comes up next, right? And so I think this is, I'm probably preaching to the choir. This is really more of a slide for the sponsors. If there's any sponsors in the room, this is my pitch to them. And in fact, I was alive, but I wasn't very, I was mostly watching Maradona and Zico in the 80s. Sorry, I just realized I'm in the wrong country to mention Maradona. I'll get in trouble. I was watching Maradona in the 1980s and Zico and Socrates, right? Am I getting the right decade? Okay. So I wasn't aware of this, but I learned from my senior colleagues that in 1980s, when the amorphous silicon TFTs came out, they were widely derided, right? People were not taking them seriously. They were saying, this is crap, this is never going to work. It turns out they're all in our displays right now. So in a way, the amorphous silicon transistors have actually changed, they're responsible for the biggest change in our interaction with computers, right? All of us have touch screens right now, and most of those are amorphous materials, amorphous silicon, ITO, and so on, right? And this brings me to Kromer's lemma. This is Herbert Kromer, Nobel Prize winner for the heterojunction, and he likes to say that the applications of any sufficiently new technology will actually be applications created by that technology. So that's why I'm very hesitant at the beginning of my talk to say, oh, we'll replace silicon. Because A, I don't think we can replace silicon, it's too good. And B, I think we'll probably, hopefully, we'll create new applications which we're probably not even dreaming of today. And again, some very, very incomplete, and I apologize if I'm missing these things. These are a few other things like phase change materials, when they were discovered, when they were commercialized. This is just very, very approximate. I could probably do time in log scale here. But phase change materials, I mean, they've been 40 years in development, and now, just as of last year, you can buy them on Amazon. Intel makes these chips, right? Jag magnetoresistance developed, I believe, in the late 80s, early 90s. IBM commercialized it about 10, 15 years later. That's actually pretty impressive. That's pretty fast. Oxide transistors, finally, they're in your iPad displays. So Apple and Samsung are using. This is also quite fast, actually, as far as I know. OLEDs. And again, I apologize if I'm missing some of the things here. I think the blue LED is actually a much, much longer story. Turns out that an American company called RCA already had working blue LEDs in 1970, but the management didn't think anything useful was going to come out of the blue LED, so they cut the project. So again, if there's funding agencies in the room, this is the story I like to tell them. We could have actually had blue LEDs probably 2 decades earlier than we did, white light using LEDs, but companies just didn't think it was good enough, and they just gave up. And then, of course, the Japanese groups came and made them commercial, and now everything is going LEDs. So these are carbon nanotubes are here, the graphene 2Ds over here. I don't know what's going to happen besides rain jackets and tennis rackets, but hopefully something good. I would like to acknowledge the students that work with me, as well as my collaborators. These are Stanford collaborators. These are the international collaborators. And hopefully one of the outcomes of this meeting will be that I will be adding many more names to this list, and I really look forward to discussions at the breaks. Thank you. I think so, yeah. Yeah. So that